Alrighty, so welcome back. This is going to be the last of the videos before the final, and I'll send 2 or 3 out with the Chapter 5 stuff, but they don't take a whole lot of time to cover. And this is Chapter 4 is what will be on the final exam. So we're going to wrap things up today by finishing up integration by substitution with some more tricks to it. Before we get to that, though, let's knock out the homework. So let's see. We're going to start with number 9. And that was the integral of 1 plus 6x quantity to the fourth times 6 dx. Well, it couldn't have made that easier if it tried. I'm looking for the piece that when I differentiate gives me another piece, and in this case, this 1 plus 6x definitely looks like what I want to make my u. So my u is 1 plus 6x, and then du, and I'm just looking at this. I do not look over here ever again. du is only here. It is going to equal 6 dx. Okay, so if I plug in over here now, I've got the integral of u to the fourth du. Alrighty, and that's important because we have to, if we have a du here, the only variables we can have over here that are allowed are u's. If I have an x here, all this has to be x's. If I have a u, all this has to be u's. So now we can do the integral. This is going to, I'm going to add 1 to this, so it's going to be u to the fifth over 5 plus c, which is going to be, when I substitute back in this 1 plus 6x right here for this u, it's going to be 1 plus 6x to the fifth over 5. And there you go. That is number 9. Alrighty, hopefully that one didn't go too badly. Let's look at number 11 now. Number 11 is going to be the integral of root 25 minus x squared times negative 2x dx. Well, again, I can see that one of these pieces is definitely the derivative of the other. If I take the derivative of 25 minus x squared, I get negative 2x. Another thing to consider is this is a root. If I try to make this my du, I don't know what root du is. I have no clue. I can do root u, but I can't do root du. So a lot of times you can use that as your guide to what to pick for your u. It's the thing that you can actually differentiate, or that makes sense. If your du winds up 1 over du, or du squared, or du to the 1/2 power, that's not the right choice. Du just has to be du. It can't be anything else. So if I make my u equal to 25 minus x squared, that means my du is just negative 2x dx. And that's what we have already up here. So now I can rewrite this as, if you will allow me, this is to the 1/2, right? So this is going to be u to the 1/2 du. Okay, and now I can do that integral. I can add 1 to u. I'm going to get u to the 3/2 over 3/2 plus c. And now I can substitute back my u, my x expression for my u, and get 25 minus x squared to the 3/2 power over 3/2, which if I really wanted to make it nice, it would be 2/3 times 25 minus x squared to the 3/2 power, right? That's your, plus c. Don't forget my c. Plus c. I'll forget it all the time, but y'all don't do that. Don't watch what I do. Don't watch what I say. It's very easy to forget that plus c, but it is important. It actually has a function there, and if you don't have it, it is not technically 100% correct. So here we go. Let's clear this and tackle the rest of it. So number 13 was the integral of x cubed times x to the fourth plus 3 quantity squared dx. Alrighty. So this one's a little more interesting. If I make my u equal to x to the fourth plus 3, that means my du is what? Well, du is just 4x cubed dx. Well, I've got an x cubed here, but I don't have that 4. So I need to put that 4 in, and the way that I do that is I'm going to adjust by putting a 1/4 outside the integral. So this is 1/4 times 4x cubed x to the 4th plus 3 quantity squared dx. And now I can match up all of my pieces. I've got my u here, and I've got my du here. So we're good to go. This, if I do my substitution, this is going to be 1/4 times the integral of, it's going to be u squared times du. And I can knock that one out. I add 1 to it, I'm going to get 1/4 times u to the 3rd over 3 plus c, which when I multiply it out is going to be u cubed over 12 plus c. And now when I substitute back my x expression, this is going to be x to the 4th plus 3 cubed over 12 plus c. That's it. And that's all we needed. That'll take care of it. So hopefully this back one went well. And again, this is just a matter of practice. It's just lots and lots of practice for u-substitution. Y'all are going to get a whole bunch of problems that you can practice on today. So let's look at the next one. So 15, we had the integral of x squared times quantity 2x cubed minus 1 to the 4th dx. Okay? Well, I've got an x cubed in this thing and an x squared on the outside, so that means I'm going to differentiate this to get this, which means my u is going to be this expression right here. So u is 2x cubed minus 1. That means du, looking only at this, is equal to 6x squared dx. I've got an x squared, but I don't have a 6x squared, so I need to put the 6 in, which means I need to take 1/6 on the outside of the integral, just like we did before. It's good to see this, though, several times until adjusting becomes just nothing. It's super easy. So this becomes the integral, 1/6 times the integral of, well, that's just going to be u to the 4th du, which we can knock that out. That's 1/6 times, I'm going to have u to the 5th over 5 plus c, which is going to be u to the 5th over 30 plus c, which when I substitute my x expression back in becomes 2x cubed minus 1 quantity to the 5th over 30 plus c. And there you have it. That's your answer. Not too bad. Not too bad. Alrighty, so let me clear this and let's tackle another one. Number 17. So in this one we have t on root t squared plus 2 dt. Okay? Again, I can't do a root du, so I know that my u has to be what's under the root. So u is equal to t squared plus 2. That means du is equal to 2t dt. Okay? So I need a 2 in front here to fulfill my du, which means I need a 1/2 on the outside. So 1/2 integral 2t root t squared plus 2 dt. Alright, now I can do my substitution, and remembering that a root is like something to the 1/2 power. So this is going to become 1/2 integral of u to the 1/2 du. Doing the substitution now. So I can do that integral. I can add 1 to that. That becomes 1/2 times, we're going to get u to the, we're going to get u to the 3/2 divided by 3/2 plus c. And when I flip and multiply, this is going to become 1/3 u to the 3/2 plus c, which when I substitute back in, it's going to be 1/3 times quantity t squared plus 2 to the 3/2 power plus c. And there you go. And this one was, when I flip multiply, it's going to become a 2/3, which will cancel those two and leave a third in the bottom. That's where that came from. Alrighty, hopefully that went well. Let's knock out the next one. We're moving now. Let's see, so the next one was 39. We started working with some trig functions. This is the integral of pi times sine pi x dx. Alrighty. Now, what do you want to make your u? If I try to make my u sine pi x, what's my du going to be? Well, it's going to be cosine pi x times pi. There is no cosine over here to fulfill the du, so that's the wrong choice. We don't want that. Okay, let's do something that we do want. What if I chose for my u? Having a very thin eraser is kind of annoying, to be honest. All right, so what if I made my u pi x? What is du then? Well, du is just pi dx, right? Because the pi is just like a 2. If the u had been 2x, the du would just be 2 dx. So we can now do our substitution over here. This is going to become the integral of, well, sine u du. And I know what the integral of sine u is. What do I have to differentiate to get sine u? Well, I have to differentiate negative cosine u to get sine u. Because when I differentiate cosine, it becomes negative sine. Negative, negative cancels and leaves me to positive. So this is my answer. I now just have to substitute back in terms of x. So this becomes negative cosine of pi x plus c. Awesome. Very nice. And if you wanted to, you could check this by differentiating. If I differentiated it, I would have negative sine sine pi x times pi. And when the dust settles, these two will cancel. I'll have pi sine pi x. And there we go. So I know that I did that right. This is the correct answer right here. Okay? So now let's move on to the last one. And we had the integral, this is number 41, the integral of cosine 6x dx. Well, it's the same situation. We don't have a sine in here as well, so we can't make our u cosine 6x, but we can make our u 6x. If we do that, what's the du? Well, the du is just going to equal 6 dx. So what do I need inside of this integral? I need a 6. So I do a 1/6 on the outside. So 1/6 integral 6 cosine 6x dx. And so now I've got the 6 dx for the du. And so I can now do my substitution. 1/6 times, well, we're going to have cosine u du. The u substitutes for the 6x, and then the 6 dx becomes du. So now I can do this integral. This becomes 1/6 times, what is the derivative? What's the integral of cosine u? Well, what do I differentiate to get cosine u? I differentiate sine u plus c, and now I just substitute back in. This becomes 1/6 times sine of 6x plus c, just like that. And there you have it. Hooray! All the homework's done. Hopefully this went well. Let me clear this, and let's get started on some of the other stuff. So let's see, where did we leave off? Oh yeah, we left off right about there. Okay, so let's say that we have, and today's just going to be a lot of practice, because that's really what everyone needs. So the integral of secant squared x times tan x plus 3 dx. Alrighty, is one of these the derivative of the other? Yeah, secant squared is what you get when you take the derivative of tan. So if I make my u tan x plus 3, why did I include the 3? Because you want to make your u greedy. If you can pull in an addition or subtraction of a constant, do it, because it's going to disappear when you take your du. So that means du is just going to be secant squared x dx. And that's everything we need. So this just becomes the integral of u du. I can do that integral because that's all an understood 1 up there. So this is going to become u squared over 2 plus c. And then I substitute back my x expression. This becomes tan x plus 3 quantity squared over 2 plus c. And that's it. That's all you need. Alrighty. So hopefully it's starting to become a little bit more sensical how to do these u-substitutions. Let's knock out another one. And let's see, clear this. Alrighty, so let's go with the integral of x times x squared plus 1 to the 4th power dx. Okay, what do I make my u? Well, I've got an x squared here and an x here. If I take the derivative of this, I'm going to get this. So u is equal to x squared plus 1. That means du is equal to 2x dx. I don't have a 2, but I can put it in. I take a 1/2 out, so this becomes 1/2 integral 2x x squared plus 1 quantity to the 4th dx. And now I can do my substitution. I've got my du part right here, and I've got my u stuff here. So this is going to be 1/2 integral of, well, u to the 4th du. And then I just add 1. So this becomes u to the 5th over 5 plus c. And then I substitute back for my u expression, which is 1/2. And this is u squared plus 1 to the 5th over 5 plus c. No, I didn't need those brackets. I just put them there for some reason. Alrighty. There you go. One more, and then we'll jump into some more complicated examples. So what if we had something really simple looking, the integral of root 2x minus 1 dx. Okay? Okay, what do I do here? Well, I've only got one thing. I've got this. That's it. There's nothing else here. So what do I make my u? The du's not here. Yes. Okay. Well, let's just go with that. U equals 2x minus 1. What is du then? Du is equal to 2dx. Aha. All I have to do in order to get the du in there is to put a 2 inside. To put a 2 inside, I just have to adjust the outside by 1/2. So this becomes 1/2 integral 2 root 2x minus 1 dx. And now I've got my 2 dx for my du substitution, and I can substitute u in right here. So this becomes 1/2 integral of, and once more, this is the same as this in parentheses to the 1/2. So this is u to the 1/2 du. Everything's in u, so I'm good to go. 1/2, and then this is going to be u to the 3/2 over 3/2 plus c. And then we're going to have, when I flip and multiply, 1/3 u to the 3/2 plus c, and now I substitute in and I get 1/3 quantity 2x minus 1 to the 3/2 plus c. And there you go. Not bad. Not bad at all. Okay, so let me clear this and let's jump into some of the more tricky examples. Okay, so let's say that we have something like the integral of sine squared 3x times cosine 3x dx. Okay, so the derivative of sine is cosine, and the derivative of cosine is sine. So which one do I make my u? Well, if I do a rewrite, hopefully it will be a lot more obvious which one. If I do a rewrite and rewrite the sine squared 3x as sine 3x quantity squared, cosine 3x dx, now I know which one has to be the u, because I can't integrate du squared. Du squared doesn't make sense. It has to be plain old du, not 1 over du, not root du, not du squared, du. So that means that this has to be my u so that this can be my du. So if this is my u, if I let u equal sine 3x, what is my du equal to? Well, my du, just looking at this, is going to be cosine 3x times 3. Okay? So I've got the cosine 3x, but I don't have the 3, which means I need to put it in here. So 1/3 integral 3 sine 3x quantity squared cosine 3x dx. And now one other quick question. Why did I make my u, as I marked the paper for no reason, what if I make my u, why did I do it as sine of 3x instead of just the 3x? Well, if I'd just done 3x as u, I would have wound up sine squared u cosine u, which I still don't know how to integrate. But by making, since both of these have their derivatives in here, I make one of them the u, the other will turn out to be the du, and I can solve that. So that's what we have right here. All right, so now that we've got the 3 solved in, I've got my du, because the du part is this times this. Oh, forgot my dx right here. Dx. So now I can do my substitution. So this becomes 1/3 integral u squared du. That whole thing becomes u squared du. And I can solve that. That becomes 1/3 times u cubed over 3, which is 1/9 u cubed plus c. Don't want to forget my plus c. And so now I can substitute the u back in. So this becomes 1/9 times sine 3x quantity cubed plus c. And there you have it. That is exactly what I need to take the derivative of to get this original piece right up here. Alrighty, and you can run that yourself if you want to. It's not a difficult solve. So, you ready to do another one? A more complicated one? Alright, what we're about to do is an advanced technique, but it will save you so many times in the future. You're going to see this pop up, and a lot of people throw up their hands and go, I have no idea how to solve this. I don't think the integral can be solved. But it can. You just have to do these steps. So here we go. Let's say I had something like this. The integral of x times root 2x minus 1 dx. Okay? Now, right off the bat, I can see what needs to be my u, because I can't do a root du, so it needs to be a root u instead. But if I make my u equal to 2x minus 1, what's my du? Well, the du is just 2 dx. Does that match anything over here? No, it doesn't. There's not only not a 2 over here, I'd still have this x out in front, because this x is not taken care of as part of my du substitution. So this is where it gets a little strange. What I've got is an expression for u, which I said is 2x minus 1, and then I've got an x just hanging out right here. Okay? When I do my u substitution, every single one of these terms has to be in terms of u. So let me show you what that would look like. If I need to have 2 dx for my du, I can do that. That would be 1/2 integral 2 x root 2x minus 1 dx. This right here is considered to be to the 1/2 power, so I can rewrite this as 1/2 integral 2x times 2x minus 1 quantity to the 1/2 dx. Now I'm going to do my substitutions in to show you what's left. 1/2 integral x times u to the 1/2 du. So the u to the 1/2 comes from this part, and then the 2 dx gives me my du, but it leaves this x here. I can't do this integral with a mixture of u's and x's. This needs to be in terms of u. Is there any way we can rewrite this in terms of u? And it turns out we can, because what I have up here is an expression of u in terms of x, but I can solve for x and get an x in terms of u. So if u is equal to 2x minus 1, 2x minus 1 equals u, 2x equals u plus 1, x equals u plus 1 over 2. So now I can substitute in for this x and get 1/2 integral u plus 1 over 2 times u to the 1/2 du. Now everything's in terms of u, but it's in a jumbled mess. So what I'm going to do is distribute this u through here and take this half out. So if you'll allow me, if I pull the half out, it's going to become 1/2 times 1/2, which is 1/4, integral u times u to the 1/2 is u to the 3/2, plus u to the 1/2 times 1 is u to the 1/2 du. And I can do this integral now. This becomes 1/4 of u to the 5/2 divided by 5/2 plus u to the 3/2 divided by 3/2 plus c. So if I flip and multiply each one of these, I'm going to wind up with, let's see, flip, it's going to wind up being 1/10, is that right? It seems odd, but I think that's right. 1/10, because the 5 would be on the bottom, the 2 would be on top, the 2 would reduce with the 4 to have a 2 on the bottom. 2 times 5 is 10. I think that's right. 1/10 u to the 5/2 plus flip 2/3. So that's going to be 2 times 3 is 1/6 times u to the 3/2 plus c. And so now I just need to rewrite it in terms of x, which I have right here. So this becomes 1/10 and quantity 2x minus 1 to the 5/2 plus 1 over 6 times 2x minus 1 to the 3/2 plus c. That's my final answer right there. And it's a lot more work when you have to do it this way, but it always works out without fail. The main clue is that my u is just an x inside of it. So the du does not have anything in there, which means I can substitute that in. No matter what this constant is, I can make that constant by taking the 1 over that constant out. And then I can just, since this is in terms of plain old x, I can resolve for x in terms of u and get rid of my x that was left over here. Okay? Maybe. All right, let's do another one. Let's see. Oh boy. Get ready. Here we go. This one's a little more intense. It's not horrible, but it's a little more intense. Let's do the integral of x squared times root 1 minus x dx. All right. Now, your first inclination might be there's an x squared here, there's an x here, so I'll make this my u, and that'll be my du. But I can't do root du. That I have no idea how to evaluate that. So this has to be my u. So if I make u equal to 1 minus x, that means du is equal to negative dx, right? Negative 1 dx. Okay. Now if I do my substitutions in here, I'm going to wind up with negative x squared u to the 1/2. Oh, sorry, I didn't mean to substitute that fast. Let me do that in 2 steps. 1 minus x to the 1/2 dx. I've got my negative dx for the du. This is going to become negative integral of x squared times u to the 1/2 du. Now I've got this x squared. Can I do anything with it? Well, I can, because now I can solve for x in terms of u. So if u is equal to 1 minus x, x is going to equal 1 minus u when I solve out and the dust settles. Okay? So if x is 1 minus u, this becomes negative 1 minus u quantity squared times u to the 1/2 du. Now I can expand this integral of 1 minus 2u plus u squared times u to the 1/2 du. And now I can distribute this u to the 1/2 through all these terms. Negative integral of, well, u to the 1/2 minus 2 u to the 3/2 plus u to the 5/2 du. Okay? Now I can do that integral. It looks like a lot of work, but it's not that bad. This is going to be negative. Here we go. This is going to be u to the 3/2 over 3/2 minus 2u to the 5/2 over 5/2 plus u to the 7/2 over 7/2 plus c. Okay, I'm going to flip and multiply. This becomes negative 2/3 u to the 3/2. Flip and multiply again. Minus 1. Wait, no, it's going to be 4/5, right? 4/5. I think I did that right. Times u to the 5/2 plus 2 over 7 u to the 7/2 plus c. And now that I've finished, I can substitute back my x expression. This becomes negative 2/3 times 1 minus x to the 3/2 minus 4/5 times 1 minus x to the 5/2 plus 2 over 7 times 1 minus x to the 7/2 plus c. And that's the final answer right there. Woo! Yeah, I know, that's a lot, but that's kind of an advanced technique. If my u is something that's just in terms of x, not x squared, not x cubed, but just x, I can always turn that around and solve for x in terms of u so that I can substitute in u's for any extraneous x's that aren't taken care of when I do the substitution. Alrighty? Okay, now, hope you enjoyed that one. Let's see, what other, we have one more kind of tricky, not tricky, but it's an advanced technique. So here we go. Hopefully you're ready for this. Let's say that I now have a definite integral. And you never have to do it this way, just this is it's a nice way to make things easy sometimes. Let's say I have the integral from 0 to 1 of x times x squared plus 1 quantity cubed dx. Okay, so I'm going to work that out. I'm going to make my u is going to be x squared plus 1. Du would then be 2x dx. And so I would have 1/2 integral 0 to 1 of 2x x squared plus 1 quantity cubed dx. And now I'm going to do my u-substitution. 1/2 integral 0 to 1 of, well, this is just going to be u cubed du, right? Okay, so now that I've got that, I can evaluate that, no problem. 1/2. All right, this is going to be times u to the 4th over 4. And this is eventually going to be evaluated from 0 to 1. But here's the deal. I can't evaluate 0 and 1 because they pertain to x's, not u's. So before I do my evaluation, I substitute the x's back in. This becomes 1, if you'll allow me, 1/8 times x squared plus 1. Now I can evaluate 0 to 1. If I do that, I'm going to get 1/8 times, well, 1 squared is 1 plus 2, so this is going to be 2 minus 0 squared plus 1 is 1. Does that look right? That looks strange. What did I forget? And that, x squared plus, oh shoot, to the 4th power. I knew it looked strange. I was like, that can't be the right answer. This is, hold on. Here we go. I thankfully found it without too much work. All right, to the 4th power now. So this is going to be 1 squared, which is 1, plus 1 is 2. 2 to the 4th is going to be 16 minus 0 squared is 0 plus 1 is 1. 1 to the 4th is 1, which is going to equal 15 over 8, right? Now, what we had to do in order to do it this way is we held the bound evaluation until we had substituted back in our x's. Then we plugged them in. But there's another way to do this. Let's say that we are back at, we have just done this part. We have done the integration. So we have 1/2 u to the 4th over 4 evaluated from. Now, this is in terms of u, but these bounds are in terms of x. But I can make them in terms of u if I use my expression up here. All I have to do is plug in what the values are. So I've got my two bounds. I've got 0 and 1 to look at. So for the first one, u equals, what does the u equal when x is 1? Well, that's 1 squared plus 1. U is going to equal 2. Now what about when x is 0? Well, that's going to be 0 squared plus 1, which is 1. So now I can evaluate u from 2 to 1. This is called the change of your limits of integration, changing the limits of integration. I've already got my expression in terms of u. If I want to evaluate like this without plugging my x back in, all I have to do is change my bounds from x bounds to u bounds. And how do I do that? I plug the x values into this expression up here to get what the u needs to be. Okay, so let's try that. So this is 1/2 times, well, if you'll allow me, u to the 4th over 4, evaluated from 1 to 2. I know I just recopied, but I want to do 1/8 on the outside because I don't want to have to do all that. U to the 4th from 1 to 2. All right, so u to the 4th from 1 to 2 is going to give me 1/8 times, well, this is going to be 2 to the 4th, which is 16, and 1 to the 4th, 1. 15/8, just like we had. So this is how you can change your limits of integration. A lot of people prefer, instead of doing the substitution back in and then evaluating, they just leave it as u and change the limits into u limits instead of x limits. Okay? I think that if you are very careful, this is fine to do, but I've seen a lot of mistakes with this. It's one of those things that sometimes I use it. 95% of the time, I just substitute my x's back in and then evaluate it using the x bounds. It's just one of those things. To me, I'm more comfortable doing this because I feel like I can make mistakes figuring out what my bounds are in terms of u rather than x. But sometimes, hey, this is an easier way to do things. It's whatever you're comfortable with. I'm never going to make you do this, but it's nice to know how to do that. If you had a super messy expression for your x's up here, sometimes it's better just to leave it in terms of u, which is usually a way simpler expression, and then change your bounds and evaluate that way. You're going to get the same answer. It's just a little more work, I think, to change your bounds. But that's just me. Whichever one you enjoy the most is totally fine. Now, this only works for if you have a definite integral where you have bounds. Doesn't apply whatsoever if you have an indefinite because there's nothing to change. There's no bounds. So, but if you have the definite integral and you want to do it this way, that's totally fine. Alrighty, let me clear this. And is that everything? Real? Yeah. Nope. We have one more piece. Aha. Don't want to forget this piece. This is actually a nice piece. This is like a bonus piece. So this is going to be integration of even and odd functions. I think you're going to like this. Okay? So if I have an even function, what does that mean? Well, it means that all of my exponents are even. So something like x to the 6th plus 3x to the 4th minus x squared plus 1. Every one of these exponents is even, including the exponent for this term, because this is understood to be multiplied by an x to the 0, which is a 1. That's actually equal to 1. So 1 times 1 is still 1. But 0 is even. So constants are considered to be even terms. So if you have an even function, what does that look like when you graph it? Well, if I graph this thing, I have absolutely no idea what this actually looks like. But let's say it looks something like this. Oh boy, I'm doing a great job. Assuming I can actually draw. An even function is mirrored across the x-axis, across the y-axis. Okay? So no matter what I put down, what the function is, if it's an even function, it's going to be mirrored. If it looks like this, the other side looks like that. Okay? So they are exactly the same. So here is the integration of an even function, what you get. So if I have an even function, let's say f is an even function. Well, the integral, I'll put it right here, the integral from negative a to positive a of f of x dx is equal to 2 times the integral from 0 to a of f of x dx. The left side is exactly the same as the right side as far as the look of the function. If I'm going from negative a to positive a, what I'm getting is the area under two pieces that are exactly the same. So no matter where I put my a, as long as it's in the negative a to a, the two pieces are exactly the same. So they are exactly, if I want to rewrite the integral, I can rewrite it as 2 times the integral from 0 to a. So it's 2 of these pieces. Well, I'm starting at 0 and going to a. Well, yeah, it just makes sense. If the left side is the same as the right side, when I integrate that, it's the same as twice the right side. Makes sense. So that's the way that you can simplify some integrals of even functions. Now, also to note, cosine x is an even function. Why? Well, cosine looks like this. It is even. If I look at it, it looks like it's mirrored across the y-axis. So you can get away with a lot of simplification if you only have to go from 0 to an a bound rather than from negative a to a. This is a much simpler integral sometimes. Okay? So that's for an even function. What's the deal with the odd functions? Well, let me show you. Let's say that we have an odd function. So what does an odd function look like? Well, an odd function looks like this. An odd function is a function that when you rotate it 180 degrees around the origin, you get the same function. So they're not, it's kind of like you can imagine if I mirrored once and then mirrored again, mirrored across the y, then mirrored across the x, I'd also get that function. But I like to think of it as a rotational symmetry of 180 degrees. But now here's where it gets interesting. If I integrate from negative a to positive a, what do I get? Well, all of this area, since it's under the x-axis, is going to give me a negative area, and all the area here is going to be a positive area. But it's exactly the same amount of area. So if I integrate, if let's say this is f, and f is odd, it's an odd function, then the integral from negative a to a of f of x dx equals 0. Because the negative area is going to cancel the positive area when I go from negative a to a. Simply because an odd function is basically the same function rotated 180 degrees around the origin. Okay? And what does an odd function look like? Well, an odd function looks like 2x to the 7th minus 5x to the 5th plus 4x cubed minus x. There are every single exponent for each term is odd. That's when you get this rotational symmetry. Okay? Now, you will be stunned at how often this comes up. Because if you see the integral, doesn't matter what the bounds are, negative pi to positive pi of, I don't know, 7x to the 5th plus 2x dx. This is an odd function. I'm going from negative pi to positive pi, so it's the same distance from the origin in each direction. I don't have to evaluate that integral. I just write down a 0 and I'm done. Same thing for the cosine was even, sine is odd, because if I look at the sine function looks like this. Right? What does it look like on this side? it is what I would get if I took the right side and rotated 180 degrees around the origin. So if I integrate from here to here, you can already see this area is negative, this area is positive. I add them together, I get a 0. So if you ever see something like negative 3 pi over 2 to positive 3 pi over 2 of sine x minus 4x cubed dx, that's an odd function. That's an odd term. That's an odd term. Therefore, it's an odd function. And this is equal to 0. Done. You are going to see this one. You won't see the 2 times the even function quite as much. But this one pops up all the time in problems in physics, and I'm sure in chemistry and some other places as well. It's just a really nice simplification right here. And that's it. That's it. So if you integrate an even function from negative a to a, it's the same as 2 times that function from 0 to a. And if you integrate an odd function from negative a to a, it's 0, always. That's it. Now, homework is going to be a sheet I'm sending to you. That sheet is going to consist of, I think it's 20 u-substitution problems. Now, you don't actually have to do any of them. What I'm going to do is send you the sheet and the answers. And if you want to kind of practice them to see if you get the same answer I did, go for it. If you don't, if you feel comfortable with it, you don't have to do the sheet I'm going to send you. You can just go straight into the take home, and that should be good to go. Alrighty, so I will be sending out, I'll be uploading this video, sending out the sheet of u-substitution problems and the take home. So you should get a lot of stuff today. Alrighty, I will be sending out a few more videos over this next week that deal with chapter 5. But as far as the graded stuff, this is going to be it. So have a good one, stay safe, and I will see you later. Bye-bye.